Imagine zooming past your fingerprint, past individual skin cells, and deep into a silicon wafer until you hit a sprawling, microscopic city. At 2 nanometers, we cross a physical threshold where the predictable rules of the macro world give way to the chaotic mechanics of atoms. The engineers building these structures are spending billions of dollars in a desperate fight against nature, trying to force silicon past a hard physical wall. For over 50 years, humanity relied on a simple premise set by Gordon Moore. Every 2 years, we shrink our computer chips to pack in more computing power. We expected this linear progress to last forever. We maintained this with a reliable architecture called a FinFET. This microscopic switch is shaped like a shark fin that channels and contains electricity perfectly. But when those walls shrink to 2 nanometers, the physical insulation fails. The electrons literally bleed through the solid barrier. Physicists call this quantum tunneling. The electrons teleport outside their containment, and the microscopic switch refuses to turn off. Because of this leak, our half-century run of predictable computing dominance has collided directly with the basic laws of nature. To stop the electrons from teleporting, engineers had to abandon flat chip designs entirely and move into complex three-dimensional geometry. This is a GAAFET, or gate-all-around transistor. The structure collapses into suspended horizontal ribbons, with a control gate wrapping around the current like a pressurized sleeve. Building upwards in three-dimensional space is the only physical workaround to keep electricity contained. Engineers are forcefully redesigning the geometry of matter to keep our technology functioning. Carving these atomic-scale skyscrapers requires one specific piece of hardware, the ASML High-NA EUV lithography system. It works by firing extreme ultraviolet light to physically print features that measure only a few atoms wide. The problem is that normal air completely absorbs this specific wavelength of light. To operate it all, the entire printing process must happen inside a vacuum simulating deep space. To focus that light, the machine relies on mirrors polished to picometer precision. If you expanded one of these mirrors to the size of the Earth, the largest physical bump on its surface would be 5 millimeters high. The global computing infrastructure now rests on the performance of a $400 million machine that pushes industrial precision to its absolute theoretical limit. Moving from the microscopic scale back up to the human level reveals the massive industrial life support system required to build these chips. A single fabrication plant consumes millions of gallons of ultra-pure water every day. This water is stripped so entirely of its natural minerals that it becomes actively corrosive to human tissue on contact. Running the vacuum chambers and extreme ultraviolet lasers demands an astonishing amount of electricity, drawing power grid requirements that rival small countries just for a single facility. The smaller our technology becomes, the heavier, more toxic, and more taxing its physical footprint is on the Earth. This colossal industrial and financial burden is concentrated in one precarious geographic bottleneck, a small stretch of land in Taiwan. This tiny island manages the specialized fabrication required for sovereign computing, effectively anchoring the global economy to a few square miles of high-tech real estate. Yet, even with billions in capital and unparalleled engineering, reaching 2 nanometers brings us to the absolute edge of what silicon can physically handle. Unless we discover a radical new material to replace it, we are looking at the final generation of traditional microchips. The 2 nanometer frontier stands as a towering, desperate cathedral built at the very